Lambda 2 is what we need to find. Lambda 1 is this thing, 1.7 times 10 to the power 1.785 times 10 to the power negative 10 equal Z1 is for copper, which is 29 minus 1 all square, and then Z2 for silver, 47 minus 1 all square. And use a calculator, we can easily get the answer lambda 2. Okay.
Xin kính chào quý phụ huynh và các em học sinh thân mến. Chào mừng đến với IB Native Learning Center và tôi là thầy Tài. Trong video này tôi xin giải thích cách để giải một bài trong đề thi Atar Physics của chương trình Australia năm 2025. Câu hỏi số 20 này là một câu hỏi về đọc hiểu và vận dụng kiến thức lý thuyết vào trong một cái tình huống thực tế, và đó là một loại bài khá lạ đối với học sinh học ở những chương trình khác, bởi vì cái nội dung cần phải đọc hiểu thì nó tương đối dài so với lại là những chương trình như A-level hay là IB. Sau đó là bài tập, là câu hỏi. Henry Moseley and the periodic table of elements. When high energy electrons are accelerated across a potential difference and fire at a metal plate in an X-ray tube, X-ray are produced. This is achieved by two methods. The incoming electrons collide with the metal atoms and lose random amounts of energy. In each collision, this energy is given off as photons in the X-ray wavelength region of the electromagnetic spectrum. This is called bremsstrahlung, or breaking radiation. The maximum energy of any emitted photon is determined by the accelerating potential difference. Incoming electrons knocked electrons out of the N1 level, and the electrons from the N2, K alpha, and N3, K beta energy levels fall to the N equal 1 level, thereby emitting photons in the X-ray region. This combination of these wavelengths is unique to the element. It is shown in the graph below, where the element's unique wavelengths are superimposed on a continuous spectrum. We have this following graph with the minimum wavelength here, slightly greater than 40 times 10 to the power negative 12 meter. The K alpha wavelength is corresponding to about 102. Do not forget the scale here, meter. And K beta wavelength is about 86 times 10 to the power negative 12 meter. A British physicist, Henry Moseley, showed that the square root of the frequency of the K alpha X-ray is proportional to Z minus 1, where Z is the atomic number of the metal. This relationship is shown in the graph below. Moseley used his relationship to arrange the periodic table of the elements by their atomic number rather than their relative atomic mass, as was previously the case. For example, cobalt Z equal 27 appears before nickel Z equal 28 on the periodic table, even though cobalt has a higher relative mass, 58.9, rather than nickel, 58.7. He did this by taking the ratio of the frequency of the K alpha spectral line for a known element F1 to the frequency K alpha line for another frequency F2. For example, F1 over F2 is Z1 minus 1 square over Z2 minus 1 square. Question A. Explain how the continuous spectrum in the graph in figure 7 on the page 36 is produced. We students studied in previous topic about discrete energy level, about the quantization of energy. So normally we know that an emission of electromagnetic wave, which are photons, are the result of the emission when electron or atoms transfer from a higher discrete energy level to a lower discrete energy level. So normally we think that energy are discrete, not continuous, such as the evidence in emission spectra or absorption spectra. However, in this graph of the emission of X-ray in an X-ray tube, we have a continuous spectrum. The explanation of this continuity is because
the mechanism of the emission of X-ray is entirely different from the model energy level. It is not the transition of electron from one higher energy level to another low energy level, except the two special characteristic emission K alpha and K beta here that I will return and explain that later. Let's focus now on the continuity of the spectrum. It is because of this mechanism mentioned here, incoming electron collide with the metal atom and lose random amounts of energy. Let me highlight that. Lose random amount of energy in each collision that between the incoming electron and the nuclei of the metal plate target. This energy is given off as photon here. This is the key, given off as photon in the X-ray wavelength. So the point is that this amount of energy that those incident electrons lose is a random amount, which means it is continuous. It can be any arbitrary value. It's not necessarily to be discrete or discontinuous. Okay, so this is my model answer. When approaching the nucleus of the target metal, incoming electrons accelerate mainly in their direction and partly their speed. Because an accelerating charged particle emits electromagnetic radiation, the electron loses some of its kinetic energy as X-ray photons. Different electrons pass nuclei at different distances and therefore lose different amounts of energy. Since this energy loss can take any value within a continuous range, the emitted X-ray also have a continuous range of frequencies. The amount of energy that an electron loses when approaching a nuclei depends on the distance between that electron and the nucleus. The closer the distance, the greater amount of energy lost by electron, because closer distance means that the interaction, the pull of the proton in the nucleus on the incident electron is stronger. Therefore, it will accelerate, will change the direction of electron motion. And that change in direction, including the change in magnitude, which means the speed also, is the mechanism of the emission of X-ray. Anytime when a charged particle changes direction, having an acceleration, there's an emission of energy, photons. It is a law of the universe that we discover and explain by the theory of James Clerk Maxwell when he unified electromagnetic radiation and electric field and magnetic field. Let's move on to question B. Explain how Moseley used his relationship to rearrange the order of certain elements in the periodic table. Let's look at the relationship given here. It is a linear relationship between the square root of frequency and the atomic number, which is the sum of the proton and neutron numbers in a nucleus. It's supposed to be a straight line which passes the origin of its graph. Before his time, Henry Moseley, scientists at that time didn't know about the structure, the specific constituents of a nucleus, which are proton and neutron, and they didn't have experimental method to measure the number of nuclei, which are the proton number in a nucleus. At that time, they succeeded in making another older version of a periodic table in which they arrange the chemical properties and some physical property also of elements in the increasing order of the atomic mass. However, the scientist Henry Moseley did this following procedure to establish that linear relationship between the square root of frequency and the atomic number Z. Here are the procedure. Firstly, he measured the frequency of the K alpha X-ray, which originated from the transition of an electron from a higher energy level to a vacancy position, vacancy state of another electron which is knocked out by the incident electron. And of course, he needed to measure the atomic number of that material, the metal he used in the experiment, and he repeat the experiment many times to measure the corresponding frequency of K alpha and the atomic number Z, so that he have lots of data. He can identify the uncertainty. He can plot a scatter graph of frequency, square root. Of course, it takes multiple steps, many trials to finally linearize the relationship between an exponent frequency and the atomic number Z, because it is not easy at all to instantly come up with the square root relationship of frequency and the number of Z. We need to do the logarithm graph to find the exponent 1/2 and finally conclude that the square root of the frequency is proportional to the atomic number Z. And then after plotting the scatter graph, we can identify that the correlation is linear. The Mesfit line is supposed to be the straight line, which passes very close to the origin within the percentage uncertainty. Correct element placed incorrectly by atomic mass. Okay, the final idea here is that if we do the old way, there is some inconsistency in the chemical properties of elements when we arrange those elements in the increasing order of atomic mass rather than the later improved version of the periodic table arranged by atomic number. Let's move on to question C. Using the graph in figure 7 on page 36, estimate the accelerating potential difference of the X-ray tip. We have the continuous graph of intensity and frequency, and wavelength, and we see that this minimum wavelength is about 41 or 42. It's not very clear to identify exactly which middle thing is 50, so I prefer the 42 times 10 to the power -12 meter for this minimum wavelength. And because we know the formula of energy of a photon is hc over lambda. C over lambda is the frequency, c is the speed of light. Okay, so here with the minimum wavelength, which is 42 times 10 to the power -12 meter, we have the maximum energy. This is the rectus energy of a photon emitted in this experiment. Okay, and this maximum energy is created, emitted by the directed loss of energy of an incident electron. Again, incident electron can lose any random amount of energy. So when an electron loses most of its energy, such as 98-99% of its kinetic energy, the corresponding emitted photon has the maximum energy here. Okay, let me write the solution down here. We have the minimum wavelength, 42 times 10 to the power -12 meter. The maximum energy of emitted photon is therefore hc over lambda. Let's substitute the value into this formula. H is 6.625 times 10 to the power -34. C, speed of light, 3 times 10 to the power 8 over the minimum wavelength, 42 times 10 to the power -12. We get that maximum energy, 4.85 times 10 to the power -15 joule. Okay, we assume that this maximum energy is very close to the kinetic energy Ke of the incident electron, like 99% of its energy, kinetic energy. Okay, which is which the electron get from the potential difference, which is used to accelerate it. Used to accelerate it, accelerate that electron. We use a potential difference V to accelerate electron, And when we multiply this potential difference, the definition is the work done in moving unit charge, which means 1 coulomb from one point to another point. So when we multiply this potential difference with the charged electron E, we get the energy that electron receives. It is electric potential energy, okay? And this entire potential energy converts into the kinetic energy. So from this relationship, we can find the potential difference required to accelerate electron to the desired energy and to create this maximum lowest frequency, lowest wavelength of the X-ray photon. Okay, so here V potential difference is the maximum energy E max here divided by the charge of electron E. Substitute the value in it. 4.85 times 10 to the power negative 15 joule divided by charged electron, which is 1.6 times 10 to the power negative 19. We get the potential difference, 3 times 10 to the power 4 volt. Let's move on to the part D of this question. The graph below shows a plot of the X-rays given off by a certain element. On the same graph, draw the plot of the X-ray emitted from the same element if the accelerating potential difference was increased without affecting the probability of ejecting n equal 1 electrons. Ejecting probability, okay. So the point is we increase the potential difference, which is used to accelerate electron. We know that the kinetic energy of the incident electron, Ke, depends on the kinetic energy of the incident electron, Ke, is determined by that accelerating potential difference, and the formula is the potential difference V multiplied with the charged electron. So when we increase the potential difference V here, the kinetic energy of those incident electrons increase as well. Therefore, the amount of energy that those electrons lose when approaching the nucleus of the target metal increases as well. That amount of energy lost by those electrons is arbitrary. It can have any value, which is why the graph is continuous. Okay, so let me write that thing. The energy lost by those incident electron equal to the energy of the emitted photons, which is hex C over lambda relationship with the wavelength emitted. Okay, so there are three effects on the graph here with the same element. Okay, the first effect is that the minimum wavelength decreases. Because of this relationship, we have now greater amount of energy lost by each incident electron, which means the energy of the emitted photon increases, and though that energy is inversely proportional to wavelength according to this formula xc over lambda. So energy increases when the wavelength decreases. So the minimum wavelength here, when we plot the new graph, the minimum wavelength will be lower than the original minimum wavelength. It is on the left here. Okay, so I choose a point here, for example. So that is the first change. Okay, the second change to the graph is harder to realize. That is, the overall X-ray intensity increases. The continuous spectrum becomes higher because energy of each electron incident can be increased, is higher than before. So the amount of energy lost also higher, and the emission of the photon energy will be higher. The result is that the overall intensity is higher. I can plot a graph like this, and it is true for the two special characteristic intensity also, which is like this. You need to focus that the starting point is almost identical here. We do not form a wider change in intensity like this. So this is the new K beta, and it decreases here to the minimum, and the overall intensity is higher. So I will draw here higher also. Okay, higher like this, and now increase to the new characteristic K alpha. It go up, huh? There, and go down. So you can see that I intentionally here draw the new K alpha with the same width. The width, huh? It's not greater, wider, I believe. And now the decrease of intensity there. So this is the new graph, and this is the new intensity of the K alpha. You can see that the position of the two characteristic emitted photon K alpha and K beta here that I drawn is the same in position here, because those special characteristic K alpha, K beta depend only on the energy difference between the levels in the target metal. It is corresponding to the transition of electron from outer layer to the inner energy level N1, which is the background basic energy level. But there's a thing here, probability of ejecting N equal 1 electron the same. Probability of ejecting N equal 1 electrons are the same without affecting it. But that does not mean that the number of electrons emitted, ejected from the N1 level is the same. Because probability and number of ejected electrons are two different things. The probability here means how likely, the chance, how many percent that an electron is knocked out from the N1 level per each incident electron. Again, per each one incident electron. Okay. However, when the accelerating potential difference is increased, the number of electrons ejected from the metal, the source, which are the incident electron, increases as well. More electron, more bullet moving toward the target, hitting the electrons or approaching the nuclei in the target means, more shooting bullet. Therefore, the number of electron ejected from the N1 level also increases. Therefore, the intensity, which is the amount of energy emitted per second and per area of in the experiment increases. That's why the intensity of K alpha and K beta here increases as well, and we have higher peaks. So let's move on to the last part, E. Using Moseley relationship, determine the wavelength K alpha line for silver, Z equal 47. If the K alpha line for copper, Z equal 29, is 1.785 times 10 to the power negative 10 meter. Give your answer to 4 significant figures. I have copied here the graph which describes the relationship between the square root of frequency and the atomic number given in the beginning of the question, and the formula stated in that part also, because it's the key to answer this question. We need to calculate the wavelength of K alpha for silver, given the K alpha wavelength for copper. Okay, so let me highlight those things and notation. This is lambda 1 for copper, and we need to find lambda 2 for silver. Okay, the relationship formula that I wrote here, I copy here. Okay, of course we have the wavelength. That formula is the frequency ratio F1 over F2, but we have this following formula. The wavelength is the speed of light multiplied with time, period multiplied with period, or C over the frequency F, which means lambda is inversely proportional to the frequency. Therefore, the ratio of frequency here, F1 over F2, is the reciprocal of wavelength, which means lambda 2 over lambda 1. Okay, and here we copy that formula, Z1 minus 1 all square divided by Z2 minus 1 all square. Now let's substitute the given numbers into this relationship formula. Lambda 2 is what we need to find. Lambda 1 is this thing, 1.7 times 10 to the power 1.785 times 10 to the power negative 10 equal Z1 is for copper, which is 29 minus 1 all square, and then Z2 for silver, 47 minus 1 all square. And use a calculator, we can easily get the answer lambda 2. Okay, 6.614 times 10 to the power negative 11 meter. Okay, so basically it's just understanding the statement from the beginning of the question and the relationship between lambda and frequency, which is the inversely relation proportionality relationship. Okay, relationship. Thank you very much for spending time and watch the whole video if you have done so. And if you have any question, please leave a comment in the comment box in YouTube video or my Facebook. Thank you very much, and I hope to see you in the next video.